Good morning. So by way of introduction, I was born in Malaysia, and during that time, tuberculosis was still quite prevalent, which tells you how old I am. So Mom was a GP, and she had her own clinic. And so every year, there would be these school kids that will line up outside to have their jabs. And I can still remember the trauma and the screaming. But worse than that, there will always be extra vaccines that she wouldn't use up. So she would bring it home and inject her kids. So I've more than my fair share of injections, which, till now has profoundly given me an aversion to needles. So that's probably why, what motivates what we do in trying to deliver medicines via inhalation, which is not new, right? The lung has large surface area, so it's there's a lot of space, a lot of area for absorption of drugs. It's also very, very vascularized. It has lots of blood vessels all around it, and so getting drugs to the systemic circulation via the lung is a good idea. Well, we all know that the body is very, very clever at trying to keep things out, and for good reason. You don't want to have foreign entities into your body, right? And so the lung is the same. It has good ways of keeping things out, and so delivering medicines via inhalation is a challenge. But of course, we're not without precedent, because we all have heard of inhalers. If you have asthma, you use an inhaler. So inhalers create aerosols of the medicines that we can breathe through breath actuation, right? But that's the problem. Inhalers require hand-breath coordination, which for the very young and for the elderly, it becomes a challenge. I was at a respiratory congress last week, and they're still talking, and inhalers have been around for about 40 years now. We're still talking about how to make it better to get medicines down the lung via inhalation through these inhalers, because the adherence and compliance of using the inhalers, having the right technique, is a challenge. You only get about 5 to 25% of people getting it right. And that's why you probably, if you have asthma, you probably know that you taste a lot of drug in your mouth, because only about 20 or 30% of the drug gets to where it is, or where do you want it to be in the deep lung. So inhalers are a challenge. Then we have nebulizers. Nebulizers, on the other hand, have an active mechanism. You can use, for example, ultrasound or compressed air to generate those aerosols for you, so you don't need that breath actuation to create those aerosols, and you just breathe them in. But as we all know, nebulizers have their challenges as well. They're large, compressed air tanks, big ultrasonic transducers, and that's why nebulizers are still pretty much confined to hospitals. Now, the recent thunderstorm asthma cases have highlighted, the need to have something portable in your house, right? The other problem with nebulizers, of course, is that the stress they exert on the drug molecules when they create the aerosol mist, because it's very, very hard to overcome, the surface tension to create new surfaces of these very, very tiny droplets, right? And as such, the ultrasonic stresses and the compressed air generate so much force that sometimes they denature the large molecules. And it's these large molecules, what we call macromolecules, that constitute the next generation in therapeutics, the biological molecules such as DNA and peptides and proteins and even stem cells. These are the next generation in therapeutics, and so we want to be able to deliver them and deliver them effectively, right? A lot of these lung cancer drugs, for example, cost a lot of money. So we're not talking about asthma drugs, for example, where, well, if you get, only about 20-30% down to your lung, you waste the rest in your mouth, that's okay because they're relatively cheap. But you don't want to do the same for drugs that cost $100,000. So you need to get them into the lung very effectively, and you need not to have that wastage, right? The other problem with nebulizers is that for a long time, the nebulization rate was very, very low. And so you would have to inhale for many, many minutes, hours, before you can get enough drug to the lung. So these represent the challenges of delivering large molecule drugs to the lung. So in our lab, we play around with nanotechnology, what you've heard, but what in particular is called surface acoustic waves, right? That's just a fancy name of 10 nanometer earthquakes. Sound vibrations, but in the form of earthquakes, right? So it's very different from sound or ultrasound, which is a bulk phenomenon. What I mean by that is that, sound goes everywhere, right? If you're behind me, you can hear me. Whereas surface acoustic waves are localized on the surface just like an earthquake. And these are the chips on which they are localized on, right? What we do, you've heard from Professor Mitchell about the technology to print electronic circuits on a chip for computer chips. Well, it's the same technology here. We put down these finger-like electrodes. And just like the shifting of tectonic plates gives rise to an earthquake, you put an AC electrical signal, and these fingers go back and forth because of the material they're made of, and they generate this nano-earthquake. And remember, this nanometer is about 10,000 times smaller than the size of your hair. So that's how tiny these earthquakes are. But they're driven at very, very high frequencies. And this is the point. They go up and down. This earthquake goes up and down 10 million times a second, okay? 10 megahertz, 10 million times a second. As they go up and down, they generate acceleration. And that acceleration is 10 million times a g-force. So as you can see from the video behind me, it doesn't take much to imagine that if you're a liquid sitting on 10 million Gs of acceleration, you're going to break up. But it's very efficient, unlike ultrasound. So we can do it on a chip with 10 times less power and very effectively create this mist. But what's more important is that these chips and these surface acoustic waves are not new to you. You use them every day of your lives, even if you probably didn't know it. Your mobile phone has 4 or 5 of these chips, and they've been used for signal filtering in telecommunications for a long time, right? But it tells you how cheap and small they can be made, because, say, if Nokia sells you the phone for $200, well, maybe $500 these days with inflation, you can be rest assured that these chips cost about 40 to 50 cents each, because they make millions of them. As Professor Mitchell mentioned, there's a way to do mass manufacturing of chips very, very cheaply these days. So we have the technology to create these mists. The other important thing to note about the high frequencies is that they do not allow time for these large molecules of drugs. They don't have enough time to unravel and shear them apart before the field reverses. So it's 10 million times a second. There's no time to pull them apart. And so almost always we retain very, very good viability of these large molecules, these biological molecules. So we have gone to sheep trials now, and the reason for sheep is not just because Australia has lots of sheep, but because sheep are large enough to share the same respiratory physiology as a human. And we did it with a DNA molecule with a surface protein raised against H1N1 influenza virus. Okay? And the idea was, well, can we deliver DNA vaccines against influenza? And the reason for DNA-type vaccines compared to your conventional vaccines is DNA doesn't require a cold chain. By cold chain, I mean refrigeration. So if you want to do third world vaccination, the transportation and refrigeration won't be a problem. It's very stable. The other reason for doing DNA is you can synthesize the vaccine very, very quickly in 2 weeks. And that's important in a pandemic because you want to be able to respond to pandemics very, very quickly. At the moment, to develop a new vaccine takes weeks and months. So we did this DNA vaccine trial, used the nebulizer, delivered it to sheep, and what we found was the sheep had an immune response that's comparable to if you were to inject, but with 4 to 5 times less dose, which makes sense because you're delivering the drug straight to your lung, where the site of infection is. And so for lung diseases, that's what you really want to do. You want to get the drug close to the lung. The platform, thankfully, it's a generic platform. Whatever we can nebulize, we can deliver. So we can start thinking about delivering different drugs, right, to treat a variety of lung diseases. It could be TB, it could be cystic fibrosis, acute asthma, or lung cancer. So we're agnostic to the drug. Moreover, the platform is also agnostic to the type of substance you deliver. So we can even think of other things, yes, aroma or scents, cosmetics. And we're even thinking of mounting it on a drone to deliver threat-neutralizing agents in the case of a biological warfare event, right, where you don't want to send personnel in. Well, send in an autonomous vehicle. It's small enough to mount it on a drone. So I hope I've convinced you that, well, we have something small, low cost, miniaturizable, that's able to deliver these large molecules effective to the lung, but without denaturing them. And I'd just like to show you a prototype that we've developed. So this is, we're grateful to the Accelerating Commercialization Grant, who have provided funding to develop a prototype. I won't show you working. I've put in some alcohol, but I don't think this would be an appropriate place to be inhaling alcohol. But we have a prototype now that's, that you can see. It's portable, handheld, and hopefully we're going to take it to clinical trials very soon, thanks to the funding that we've received. So in summary, we hope that this will provide us a way that will revolutionize the way we administer our drugs in the near future. Thank you very much.